Welcome back to Columbia Physics Preceptor Television. Today I will be giving an example introduction for the third optics experiment, the one concerning optical instruments. So welcome back, everyone. Last week we saw that we can use the principles of optics and thin lenses to create real and virtual images of objects. We can bend light, focus it, and defocus it sort of as we please. That was the first look at applications of the laws of optics. Today we'll be looking at more real-world examples. We'll be looking at a magnifying glass, how the eye works, and also try to build a microscope to look at very small objects. Last week we mentioned the term magnification. In that sense, it was used to compare the size of an object versus the size of an image. This can be considered linear magnification. By actually measuring the physical size of the object and the size of the image, we're able to get a value for the magnification of the lens system. Today we'll be talking in a little bit more general terms. There are two kinds of magnification. The first one is linear magnification. The second one is angular magnification. You can think of this by imagining that an object in the distance makes a certain angle with your eye, where if you were to draw a ray of light from one end of the object and the other end of the object back to your eye, what is the angle alpha that object or that those rays of light would make? We can think of magnifying an image in an angular sense by simply causing it to take up a larger angle with respect to your eye. Now, the eye is probably the optical instrument that we're most familiar with, since it does, in fact, consist of a lens at the front of the eye and then a screen at the back onto which an image of the real world is projected. In order to see very small things, we would like small objects to take up a very large angular size. Probably the easiest way that we accomplish that is by moving the small image very close to our eye. However, the eye has its own physical limitations. There's something called a near point. This is the closest point with respect to the eye at which we can place an object and our eye is still able to focus on it. For most humans, this is about 25 centimeters. Today you will be measuring your own near point, and you will probably get a distance less than 25 centimeters. This is since here at Columbia we're mostly young folk, and our eyes are still very flexible and able to adapt to closer objects. The way you'll go about measuring this is by taking an optical rail, placing it close to your eye, and then placing a small screen with grid lines on it, and sliding it closer and closer to your eye, very slowly, until you get it to a point where you can't quite focus on it. You should try to find the point. You should try to find essentially the near point of your eye. This is the place or the distance along the optical track where you can place the screen very, very close, but have it still be in focus. The second optical instrument that we'll be looking at is the magnifying glass. Now, since the eye's near point is finite, sometimes we would like to see smaller things, but we can't get them close enough to our eye for their features to take up a very large angular size. What you can use is just one simple lens. In this case, a convex lens with a focal point or with a focal distance f. If we place an object directly at the focal point and then have our eye on the opposite side, we'll actually be able to see a virtual image of this object. We can use ray tracing diagrams to express how this works. Remember that any light passing through the center of the lens is not bent, and any light that goes parallel to the lens comes out and goes through the focal point on the other side. And this drawing is not quite good, but we can see what happens. The rays of light from the tip of the object enter the lens and then actually come out parallel. This parallelization of the rays of light makes it seem like they're coming from a distance far, far away. Like this object is far enough away that all of its light rays are coming in nearly parallel to our eye. What we end up seeing is an object, or is an image rather, that takes up a very sizable angular size, but is at infinity, so that moving our head small distances back and forth doesn't seem to change the angular size of the object. We can express the magnification that we see using the angle alpha that this image or the object subtends in front of our eye. For a reference of angular size, we simply use the near point of the eye. In this case, the angle alpha is just the inverse tangent of the object's or the image's size divided by 25 centimeters, the near point of the eye. When we run the image through a magnifying glass, we then see a magnified angular size. Call it alpha prime. In this case, it's the inverse tangent of h over the focal length of the lens. We can equate these two together to get an expression for the angular magnification, which is simply h over f divided by h over 25 centimeters. And by rearranging terms, this comes out to be 25 centimeters divided by the focal length of the lens. Now, to measure this in practice, we do need some sort of reference for the angular size. What we'll use is a lens with a 25 centimeter focal length placed on an optical rail, looking at a screen 25 centimeters away. When you look at this, you will see the image magnified, but we'll define this as simply our unity of magnification. This is a magnification equal to 1. What we'll then do is construct another perpendicular optical rail with another screen and a lens of an unknown magnification. We then like to put a half-silvered mirror across one end of the optical rail such that when you look at the mirror with your eye, you see an image both of the reference screen and of the magnified object screen over here. You can then compare the lines on these screens to get a measurement for the magnification. On one screen, you'll see the lines rather close together. On the other screen, you'll see other lines, the dotted lines, at a different distance apart. By estimating, or by measuring rather, the number of lines between the reference lines, you can get a value for the magnification. The second optical instrument that we would like, or I should say the third optical instrument that we would like to examine is actually the microscope. This is a bit more complex than the simple magnifying glass, as it uses two lenses instead of one, but it allows you to get greater angular magnifications of objects. To construct a microscope, again, we can use ray tracing to examine how one works. You start with one lens, call it the object lens, with a focal length large f. If an object, a very tiny one, is placed greater than the focal length away, as you saw last class, this will create an image on the other side of the lens, a real image. What we can then do is parameterize this object as being a distance s away from the first lens, and its image is a distance s prime on the other side. You saw this before. What we can then do is place a second lens precisely so that its focal length, little f, its focal point, is exactly on where the first lens creates its real image. This image then acts like an object for this second lens. And what you see, looking at the other side, is a virtual image out at infinity, and very much magnified, you're seeing the image of the image. The image that you see is very large and inverted with respect to the original object, but it's at a larger angular magnification, so we can actually see it. This magnification can be expressed using two ratios. First, S prime over S to account for the magnification of the objective lens, and then 25 centimeters over F to account for the magnification of the eyepiece. To examine this and take a measurement of the magnification, we'll use a similar procedure to that of the magnifying glass, where we have a reference rail and the microscope rail perpendicular to each other and look through a half-silvered mirror. You should note there is a slight typo in the lab manual. The picture that describes how to put together the microscope is slightly inaccurate. It describes S plus S prime as being something like 35 centimeters, when really it's more like 50 centimeters. Also, you should note when you're doing the experiment that the screen at the end of the microscope has 2 lines for every 1 line on the reference plate. So when you're doing your calculations, you may easily be off by a factor of 2 unless you take that into account. Again, as with all optical experiments, getting all of these distances right can be a little frustrating, but if you're patient, you should be able to get very good measurements of the magnification along with estimated uncertainties. That's about all I have to say. Have fun.